So the next topic is Bernoulli equation, and this is the definition. An equation of the following form is called a Bernoulli equation. Let's see the equation. dy dx plus p of x times y equal to q of x times y to the power n. So you can clearly see that it looks almost like a linear equation. The only difference is here. In a linear equation, we have all these things, but the y to the power n part is not there. And as a result, note that a Bernoulli equation is just a linear equation if n is 0 or n is 1. That means a linear equation is a special type of Bernoulli equation. Now the next natural question is this: how can we solve a Bernoulli equation? This next theorem tells us how. Suppose n is neither 0 nor 1 because of this thing. Otherwise, our Bernoulli equation is just a linear equation and we already know how to solve linear equations. So, say n is neither 0 nor 1. Then the transformation v equal to y to the power 1 minus n turns or reduces the Bernoulli equation into a linear equation in v. In v means v is the new dependent variable. So, once you apply this transformation, this equation gets turned into another equation involving the dependent variable v and independent variable stays x, and that equation is linear, and then you can solve that. A proof of this result is available in the book, of course, and it's nothing really very difficult. You consider this transformation and then differentiate both sides with respect to x using the chain rule. So that way you will not only have something to put here in place of y, but you will also have something in place of dy dx, something involving dv dx. So that way the equation will get turned into another equation involving v and x that will be linear. So the proof is just that. Okay. So instead of going into that, we next see example 217, where we now have to solve this equation. This is not linear, but it's a Bernoulli equation. So you can see that here n is 3. So let's go through the process. I mean, this is the process. So first we apply this transformation to this one. It will get turned into a linear equation, and then we will solve the linear equation. We start the solution like this. Instead of simply considering the given equation as it is, we change it slightly. We turn it into this equivalent form by multiplying both sides by y to the power minus 3. So that way you get y to the power minus 3 times dy dx plus y times y to the power minus 3 is y to the power minus 2. That is equal to x. Alright. And then we apply our transformation. V equals y to the power 1 minus n. In this case, n is 3. So that is y to the power minus 2. And then you differentiate both sides with respect to x, the thing that I said just now about the proof of that general theorem. That same procedure you go through. So the left hand side will be dv dx. Now to differentiate the right hand side, you will have to apply the chain rule. So first you differentiate y to the power minus 2 with respect to y. Okay, that is the chain rule. So doing that, you get minus 2 times y to the power minus 3. By the power rule, you already know these things from calculus. And then you multiply that by the derivative of y with respect to x. So that way you get dv dx equal to minus 2 times y to the power minus 3 times dy dx. And then you divide both sides by minus 2. Both sides of this equation by minus 2, that way you get this. So you see that you are actually getting something for this part, and that is why we in fact multiply both sides by y to the power minus 3. That is, we changed the given equation. So now what will you do? Now you have all the ingredients, you just have to put them in place. In place of this, you are going to use this, and that involves v and x. Y will vanish. Here also, in place of y to the power minus 2, you will write v. So that way the equation will get turned into an equation involving v and x. And the theorem ensures that that will be linear. Let's see how it goes. So star becomes, we have given it some name, some label, so that we can refer to it. So star becomes this. Now it is still not exactly in the form where you can call it a linear equation, but we are almost there. Now multiplying both sides of this equation by minus 2, this is what we get, dv dx minus 2v equal to minus 2x, and yes, this is linear, and this is the linear equation with integrating factor e to the power integral of minus 2 with respect to x. Why? Because in a linear equation we have dv dx, if the dependent variable is v, dv dx plus p of x times v equal to q of x. In this case, p of x is minus 2, the constant function minus 2, still it's a function of x. So that is why this is the integrating factor, which of course becomes minus 2x after you do the integration. So this is our integrating factor, e to the power minus 2x. So next, of course, we are going to multiply both sides of this equation by this integrating factor. So multiplying both sides by e to the power 2x, both sides of the above equation, we get this, of course, e to the power minus 2x times dv dx minus 2 e to the power minus 2x times v equal to minus 2x times e to the power minus 2x. And you know already that if you multiply such a linear equation by its integrating factor, this is what the left hand side becomes automatically from theory. The derivative of the integrating factor times the dependent variable. And the right hand side, of course, it remains like this for now. And then we integrate, because we have got a derivative on the left side. So if we integrate, we are just going to get this function, e to the power minus 2x times v. And the right hand side will be the integral of this with respect to x plus an arbitrary constant c. Now it turns out that this integral is just this, 1 over 2 times 2x plus 1 times e to the power minus 2x. Exactly how this is equal to this, I am leaving that to you, because this is not our main aim. We are not trying to learn integration here. We are just using integration. To see why this is equal to this, you can understand what you have to do. You have a product of two functions, so you have to, you can use integration by parts, or to just simply verify that this is the integral. You differentiate this and see if you get this. That's just it. So where c is an arbitrary constant. And now, of course, although we have got a one parameter family of solutions, but it has v. But we originally had y. So now we have to bring back y. Now before bringing y back here in place of v, we simplify this equation a little bit, and that gets us this. What did we do? We multiply both sides by e to the power 2x, so that the left hand side now is v, and here also there will be no longer e to the power 2x. If you multiply 2x plus 1 by 1 over 2, you will get x plus 1 over 2, and with c you will have 1 e to the power 2x. And then we recall what v originally is. V is y to the power minus 2, or 1 divided by y square. So that way you get this one parameter family of solutions of the original differential equation, which is the Bernoulli equation, and where of course c is the parameter. The section ends with a note where we are next considering this general type of equation. It looks complicated, but let's try to see the individual parts carefully. You see two derivatives multiplied here, their product. One of them is df of y dy, that means the derivative of some function f of y with respect to y times the derivative of y with respect to x, plus p of x times f of y equal to q of x. P and q are, as usual, known functions of x only, whereas f is a known function of y only. We do not really know y as a function of x. In fact, that is why the question of solving this differential equation comes in the first place, because we don't know y as a function of x. We only know that y is the differentiable function of x, which function that we don't know. In fact, that's how the solutions come. In spite of not knowing y, we know f as a known function of y. For example, in place of f of y, you can have sin y, say for example. Okay, so like that we have this equation. Now here, if you just simply give a name to this f of y, because f is a function of y, so there will be a dependent variable for this function also. Let's call that v. Say v is equal to f of y. Now if you differentiate both sides of this equation with respect to x, then the left hand side will be dv dx. To differentiate the right hand side, you will again have to use the chain rule. So you will first differentiate the function f with respect to y, which is how you get that derivative, times the derivative of y with respect to x. So in place of this, now you can put dv dx plus p of x times v is equal to q of x, which you can clearly see is a linear equation in v. So you can see that although originally the differential equation looks quite complicated, but just by naming f of y v, we see that it's nothing but a linear equation in v, not in y, okay, in the new variable v. And now there is a link with Bernoulli equation also, and that link is this. The Bernoulli equation is a special case of this equation. I did not write anything here because I did not name, I haven't given it any name. So is a special case of this equation. Let us see how. So we then proceed like this. It has the following equivalent form. It means the Bernoulli equation. You get this one from this one obviously by multiplying both sides by y to the power minus n. In fact, recall that we solved that example also like this. But anyway, next part we do, we multiply also both sides by 1 minus n. Actually, we could have done both these things at once, but anyway, we ultimately have this equation. Why are you able to multiply both sides by 1 minus n and still say that this is equivalent? Well, when you are doing multiplication, there is no problem. It is when you do division that there is a problem, that whatever you are dividing by should not be equal to 0. N is not equal to 1. That is why you can go back. Just like you can multiply both sides by 1 minus n to get to this equation, you can also go back. That is why it's okay to turn this equation into this one and still say that they are equivalent. But now what is the point of making this more complicated? And that is this. We are not intentionally making it more complicated just for nothing. We next write this equation itself like this. This part stays the same, 1 minus n times y to the power minus n times dy dx. But then we write plus p1 of x times y to the power 1 minus n equal to q1 of x, where p1 of x is 1 minus n times p of x and q1 of x is this. And then you also note this fact that if you differentiate y to the power 1 minus n with respect to y, you get 1 minus n times y to the power minus n. And now you go back to that equation where the note starts and consider y to the power 1 minus n in place of f of y, a known function of y. So this part becomes d f of y dy. So that's how our Bernoulli equation also is in that form. That means Bernoulli equation is also a special case of that general equation.